Okay. All right. Thank you very much. Thank you all for coming. Thank you for the opportunity to speak here. It's great to be at this program. So I'm going to talk about some work that's joint with Christine Bauer and Matthew Burke, who are both at Calgary. So this is about Goodwillie's calculus of functors. Very quick few things about that. The calculus of functors is some techniques that try to apply ideas and concepts from ordinary calculus to homotopy theory. In particular, using calculus ideas to study functors and their approximations with polynomial functors and things like that. And the goal of this talk is to try to make the analogy between what you might call ordinary calculus and functor calculus more precise. And the basic plan is to give a common category-theoretic framework that encompasses both ordinary calculus and calculus of functors. And that will allow us to more easily say what this analogy consists of. Okay, so that's the basic plan. I want to say a few words about how I sort of came to this project. And a few years ago, I started noticing some papers on the archive with titles involving things like differential categories. And some of the people writing about these things, Luke, Cockett, Ching. And I saw the name differential category, and I thought, well, this must have something to do with the calculus of functors. The words more or less match up. So this should be something that I need to know about. And so I tried to read these papers, and I found that that these people are computer scientists. And my eyes glazed over when I tried to read these papers. They involve words like modality, which I didn't understand. And so I had a lot of trouble. So I kind of gave up on trying to understand whether this was actually connected to the calculus of functors. So then, somewhat later, more recently, a paper appeared by Christine Bauer, Brenda Johnson, Christina Osborne, Emily Reel, and Amelia Ted. And one of the claims made in this paper, I'm sort of paraphrasing a little bit, but the claim was abelian categories form a Cartesian differential category. And so this paper really helped me sort of understand in language written by homotopy theorists what a differential category was. And moreover, that this, the substance of this paper is really calculus of functors from more or less Goodwillie's perspective. So it's stated about abelian categories, but it's really chain complexes of abelian categories, and this is calculus of functors. So what I want to do today is to talk about this joint work, which in some sense extends the work of the Bjort paper. And the slogan for this extension, so today, the slogan is going to be presentable infinity 1 categories form a tangent category, or a tangent infinity category. And so the main part of the talk, I'm going to try and tell you what a tangent infinity category is and how the presentable infinity 1 categories form such a thing. The basic answer, and that's what I'll start talking about, is that a tangent category basically tells you how to axiomatize the tangent bundle functor. And so I'll sort of show you, again, more of this analogy between how that works for ordinary smooth manifolds and presentable infinity one categories. Okay, so that's more or less the plan. All right, so the first thing I want to do is try to lay out the beginnings of this analogy, which will also sort of tell us the beginnings of the structure of a tangent category. So here is sort of an analogy between ordinary calculus and the calculus of functors. So on this side I'm going to put manifolds, and I think there's a couple of columns here, and on this side I'll put infinity one categories. This is the calculus of each of these things. So on the manifold side you might study a smooth map between manifolds. See if I can not stand in front of this. So you might study a smooth map between manifolds, and in calculus, the analog is we want to study a functor between infinity categories. Okay, so pretty much the first thing you learn in differential geometry is, so once you have the notion of a manifold, you need its tangent spaces. So what is a tangent vector? So a tangent vector, V in the tangent space to a manifold of X, is a equivalence class of a smooth curve. So gamma from the real numbers to M is a smooth curve with the property that gamma of 0 is X, and we say that two curves are equivalent if, well, this is sort of the definition essentially, but if they agree on their first derivatives. So this is saying that a tangent vector is capturing the first derivative of a curve at the point x. So what does this look like on the infinity category side? So I'm just going to try and translate this as clear as directly as possible. So a tangent vector. So V is now going to be in the tangent space to an infinity category at an object of that infinity category. Okay, so C here is an infinity one category, X is an object. And I should take equivalence classes of gamma, where gamma is a functor. So I'm going to replace the real line with spectra. And actually, I'm just going to write finite spectra there, avoid having to keep saying everything preserves filter colimits. So I'll just put finite spectra in place of the real line. So I have a functor from finite spectra to C, and gamma of the trivial object should be my object X. And then I want to tell you the equivalence relation. The equivalence relation should be that two curves agree up to first derivatives. So gamma 1 is equivalent to gamma 2 if the first Goodwillie approximation P1 of gamma 1 is equivalent to P1 of gamma 2. So in the sort of category theoretic world, we have a sort of different way to form equivalence classes, and that's localization. So really, what I want to do here is localize the category of all of these functors at these equivalences, and when I do that, what I get is just the one excisive functors. So a cleaner way to say what a tangent vector is so V is a one excisive functor from finite spectra. Okay, so that's our analog of a tangent vector.
You didn't say what Q1 is. hopefully is what I think it is, but are you using some like completeness assumptions on C?
I'm using that it's presentable, I suppose.
Ah.
Yes. So yes. Yeah. So let's.
So you take the colon or Sn and then loop it down again.
Exactly. Yeah. So P1 here is Goodwillie's construction of the excisive approximation to a point. Okay. So that's the analog of a tangent vector, and now if you put all the tangent vectors together, you get the tangent bundle. So we have the tangent bundle. Tangent bundle is a bundle. It comes with a projection from Tm to M, and on the category side, we have the tangent infinity category, which I'll write as just a collection of all the excisive functors from finite spectra to C. And it comes with a projection that just sends V to V of the trivial spectrum. So this definition of the tangent bundle of an infinity category is it's not new at all. This is so in this form, or almost this form, it's described by Lurie, but the ideas go back much further than that. I guess I also want to like Goodwillie here, because a lot of the intuition behind the analogies that I'm talking about today come from ideas of Goodwillie in terms of what the connection between calculus functors and ordinary calculus is. So probably there should no doubt be lots of other people here as well. Okay, so we have the tangent bundle. So if we're going to do now calculus with smooth maps, then we should observe that the tangent bundle is a functor. So, so we have for a smooth map, we have this total derivative, which is another smooth map from on the tangent bundles, and on this side. And you can say what this is. It takes the equivalence class of a curve gamma, just for the equivalence class of composing gamma with f. And then on this side we have a very similar picture. So if f from c to d is a functor, then t of f from tc to td sends v to, well, I can compose v with f, but the result might not be any more excisive, and so I should take P1 of that. And it's not entirely trivial, but you can show that this makes T into a functor. So T, so on this side, T is a functor from the category of smooth manifolds to itself, and on this side, it's from some category of presentable infinity categories to itself.
But there isn't really any condition like smoothness, it's any function.
It's any functor. Any functor. Right. Any functor that preserves colimits. Maybe that's the preserves filter colimits. Maybe that's the analog. Okay, so we have this tangent bundle functor, and so now the a tangent category is essentially going to consist of a tangent functor like this, together with some additional structure and a lot of axioms that need to be satisfied. So what additional structure does the tangent bundle have? So on the manifold side, we know a lot of structure that the tangent bundle has. We have addition of vectors, and we have a zero section. In fact, we have a vector space structure. It's a vector bundle. On the category side, there's analogs of some of this. So I'm going to sort of just write sort of the nature of these things. I have an addition of vectors, and I have a zero section. And I think I'll just leave you to try to figure out what those are if you're interested. It's not particularly difficult.
Then say it, please.
I can say it, okay. So this zero sends an object to the constant functor of that object, and this sends two excisive functors that agree on the trivial spectrum to their product over that trivial spectrum, over the image of that trivial spectrum. Okay. So
Are the fibers of this plus functor stable?
they are exactly, yes. So that's probably, let me sort of suggest why that might be the case. So we have a sort of a scalar multiplication on the manifold side, which you could think of as giving you an action of the presentable infinity category spectra on the fibers, which makes those fibers into stable infinity categories. So I should say this somewhere else maybe as well. The TXC is a stable infinity category.
Is it always a stabilization of the O and other?
Yes, exactly. So far I think of this as sort of the superficial structure of the tangent bundle. And if that was the extent of the analogy, then I don't think this would be such an interesting talk. Maybe I'll leave it for you to judge whether at the end whether you think it becomes any more interesting. But certainly we want to go a bit deeper than just saying that we have a sort of bundle of stable infinity categories. So there's
So is there any precise meaning to the bundle? Is there a local triviality condition in any sense?
Not exactly, no. So, well, I'm going to give you another property. Okay, and I think it's not an obvious property. It's, yeah, I don't know exactly how you would talk about the local triviality, but this is the additional property that I want to talk about. So, so let me just call this more structure on the tangent bundle of the manifold. And so here is a lemma that will capture what this structure is. For any smooth manifold, there is a pullback square in the category of manifolds that looks as follows. So I have so essentially this more structure that I'm interested in is structure on the iterated tangent bundle. Okay, so what happens when you take the double tangent bundle of a manifold? Well, this is one of the things that happens. So I can look at this pullback of so projecting onto one of the inside tangent bundle here over the zero section, and that pullback is just this fiber product of two copies of the tangent bundle. How to think about this lemma? So in particular, let me just show you the fiber over each individual point here. Actually, let me try and draw a picture of this. So here is my manifold M. It's a one-dimensional manifold in this picture. And so the tangent bundle of M is a one-dimensional vector bundle over M. And at each point X, I have a fiber, which is just a copy of R. And so I can now take a point in the tangent bundle, so that's a tangent vector at x, and ask and look at the tangent bundle to Tm at B. And so in this picture, that's going to be, let me draw that as a sort of, something looking like this. It's the tangent space to Tm at B. So this is Tb Tm. So T squared of m is the collection of all of these tangent spaces. And what am I interested in this lemma? I'm interested in something that when you project down to m, you get the zero vector. And so in this picture, what that corresponds to, it corresponds to a tangent vector that is vertical over x. So when I project down to m, it's the zero vector. So I'm interested in something like that. And well, something like that is really in the it's in the tangent bundle of the tangent space. So that vector is tangent to the tangent space. So it's in the tangent bundle of the tangent space. And tangent space is just a vector space, so its tangent bundle splits. It's just txn cross txn. So a vector here is determined by giving its base, which is v, and then some other tangent vector u. And so we have this splitting.
This is work just the same if you have any smooth vector bundle over. It wasn't really the tangent bundle that was relevant anywhere.
Well, this so certainly this property is just about having a vector bundle. This lemma says that these splittings are pieced together in a particular way. So I can't say I totally understand exactly the significance here, and yes, there's definitely a corresponding picture for general vector bundles, but this is the property of the tangent bundle functor that I want to add to the definition of a tangent structure. So, okay, so based on that lemma,
It does saying that the tangent bundle is the normal bundle of the diagonal.
I don't know. Yeah, I don't know. Okay, so I'm going to, based on this, give sort of a first definition of a tangent structure. So this is due originally to Rosicky in 1984, but then developed a lot further by Cockett and Cruttwell starting in 2014. And so they've really sort of taken Rosicky's definition and expanded on the sort of theory that you can develop abstractly inside a tangent structure. So here is very roughly what their definition says. A tangent structure on a category X consists of, so an endofunctor plays the role of the tangent bundle. A projection says that it is does live over the identity functor. And then I don't want to try to spell out everything here, but so part of it is the addition and zero construction. So we just try to summarize that by saying we have a fiberwise internal commutative monoid structure on T, which says you can add vectors and you have a zero vector. Notice there's no negatives here, so we're not including negatives of vectors. And then let me add one more thing. There's stuff that I'm not telling you here because there isn't time to go into it, but I want to add in a natural map L like this that makes this square into a pool. So L, which goes from sort of T crossover the identity T to T squared, such that star being this. So this is the definition given by Cockett and Cruttwell for a tangent structure on a category. And I should also say, I mean, there's a lot of commutative diagrams in this definition that I'm not going to try to tell you about. There's lots of conditions about how the different pieces of the structure they describe interact. So,
what's the example they were interested in other than smooth manifolds?
Yes, examples. So one, smooth manifolds. Example 2, schemes, where T of X is the Rosicky tangent property. So the example that I think they're most interested in is examples that come from synthetic differential geometry. So we say the infinitesimal objects in a model of synthetic differential geometry. So synthetic differential geometry, as I understand it, which is not very well, is a sort of much more sophisticated attempt to understand the structure of to understand differential geometry on manifolds from the point of view of logic and topos theory. And so a tangent structure is a sort of a weaker theory than that. So any model of synthetic differential geometry provides you with a tangent structure, but the synthetic differential geometry goes further, and I don't know enough about it to tell you more about that. I think this is probably the example they're most interested in, though. That and the next one, which is that any Cartesian differential category and in fact, so I mentioned earlier the Bjort paper, which says that abelian categories form a Cartesian differential category. So and one of the things that's pointed out in that paper is that in fact there is a tangent structure on abelian categories in that context.
What is it?
It's
T of an abelian category.
Sorry, what is
T of an abelian category?
T of an abelian category is the abelian category cross itself. It's the square of the abelian category.
Just their fine space.
And the explanation for that is that abelian categories in this context are just vector spaces. They're the analogs of vector space. They're stable infinity categories, right? So So T of any stable infinity category, maybe I should have put this up earlier. If C is stable, T of C is C plus C. And so this is in particular true in any differential category.
What's the differential category?
Differential category is defined as a category with a sort of a differential, which is a way of starting with a morphism and producing a sort of morphism like this. So subject to 7 axioms, I think, which are all inspired by ordinary derivatives. But this is meant to be the analog of differentiation for maps between vector spaces. And so number 4 here is just saying that vector spaces are a particular example of manifolds. That's one example of number 4. Okay. All right, so what we want to do is infinityize this definition. It's not in a very nice form for being infinityiized because there are lots of commutative diagrams. And commutative diagrams are not things you want to try to deal with when you get into the infinity category theoretic place. So fortunately, there's a different characterization of tangent structures that is much more amenable to being transported into the world of infinity categories. So let me try to explain this, and this will actually allow me to give you a completely precise definition of a tangent structure. So number 3 title is they algebras. So this is due to Leung. This particular definition and the theorem that follows it is due to Leung. And so Leung defines they1 to be a certain subcategory, so the full subcategory of the category of augmented commutative n algebras. So these are algebras over the natural numbers. So these are semi-rings, or rigs, not full rings. So it's the full subcategory of this category containing the following objects. So I'm going to label this object WK, and this is just given by taking K generators and then quotienting by all the quadratic relations. So this is for all pairs of I and J.
So what's quotient now if you don't have inverse?
It's a convenient notation for saying that I have.
If you set them equal to something, do you set them equal to 0?
These are equal to 0, yes. So.
But that's fine. It's just a coordinate.
Okay. Yes. So this, all quadratic things here are 0. So I have my basis as a, I have a 1, and then I have each of the, single variables, and that's it. That's my. But
how is this augmented?
It's augmented just by mapping to n by setting all of those to 0.
So it's really just square 0.
Yes. Yeah. Exactly. This sort of k-fold square 0 extension of it. So I have those objects, and then I have finite tensor products of these. collections of generators like this for any finite number of collections. Okay, so the objects in this category are quite easy to understand, and the morphisms take a little bit more thought. You have to kind of think, when do I have a morphism between two objects like this, and what, obviously such a morphism is determined by what it does to the generators, and then you have to think, where could the generators go? You have to satisfy the relations. Okay, so I have this category, and so here is the theorem of Leon, which says that tangent structures on category X uniquely correspond to monoidal functors from this category of A algebras under the tensor product, where the unit is n, to the category of endofunctors on X under composition. Uniquely correspond to monoidal functors like this that preserve certain pullbacks. So this functor that I labeled T dot, this captures all of the structure that we have in the tangent structure on X. The projection, the commutative monoid structure, and so on. But there are conditions that this has to satisfy, most notably that lemma that I told you about earlier. So what does that correspond to here? It corresponds to a certain pullback in this category of A algebras that has to be preserved. So I'll write down what that pullback is. Once you sort of figure out how to translate between these diagrams in this category of A algebras and the sort of diagrams telling you what happens with the tangent bundle, you can sort of see that this corresponds to the lemma, the pullback we had in the lemma earlier.
Are you sure the n and the w prime are in the right? It's like different from the tangent bundle.
So n. Let me try to explain this a little more. So T n.
Isn't n the manifold and w the tangent?
No. Yes, n is the manifold. So Tn is the identity. So the diagram we had before looked like this. It was n going to Tm, T squared m, and this Tm crossover n with Tm.
The W used to be the other side. W2 and W1.
That was my question. Yeah.
Oh, at the top?
One of the two things are in wrong order.
It
So
doesn't seem to be
the
map.
tensor product corresponds to composition. So this tensor product is the thing that's sent to composition. So T squared is W1 tensor W1. It looks wrong because of the notation for co-product versus product. This W2 is the product of two copies of W1.
So in W2, x1, x2 is 0, but not in W1 tensor W1.
Yes. That's right. So here x1, x2 is 0, and here this is just sort of, I just have two generators.
How could you have a morphism then?
Right, so that's the interesting part, is what is that morphism? That morphism is not just x1 goes to x1 and x2 goes to x2. I think you can describe it as x1 goes to x1 and x2 goes to x1 plus x2 or something like that. Sorry, I didn't write this down in my notes, unfortunately. Let's see.
But you need another element that squares to 0, and unless there's some greater commutativity, where does this come from?
I think it's x1, x2. So x1, x2 squares to 0, and when I multiply these together, I also get 0. So x1, x2 maps to 0. Okay. And you can use this. I mean, if you work out, check that I'm getting that right, you can use this to sort of figure out what that map is in the lemma that I described earlier. It's not totally obvious to write down that top map. Okay, so this theorem allows us to define tangent infinity categories in a very simple way. Well, okay, I say simple, but I'm going to make it as complicated as possible. So this is part of our joint work. I'm going to take this opportunity to define a tangent structure in as sort of great a generality as I can think of, in such a way that includes just a tangent structure in an ordinary category. And so here is, and this might be going too much, but we'll see. So I want to start with an infinity 2 category and an object in that infinity 2 category. And the point of an infinity 2 category is that it's enriched in infinity 1 categories. So if I look at the endomorphism object of X, then that will be an infinity 1 category, and it will also be monoidal under composition. So n of X is because of this, it's a monoidal infinity 1 category. And so now I can define a tangent structure on X just by analogy with the theorem up there. So tangent structure on X is a monoidal infinity 1 functor. And so I'm just here going to take just the nerve of the category of A algebras. So this becomes a monoidal infinity 1 category. So a tangent structure is a monoidal infinity 1 functor like this, and I just ask that it preserves the same pullbacks. So the same pullbacks that appear in Leung's theorem, I'm just going to ask that they're now taken to pullbacks in this infinity 1 category. So preserving the same pullbacks. In particular, that one up there. So as an example, I can take C to be an infinity 2 category of 1 categories. And 1 categories form a 2 category, which I can think of as an infinity 2 category. And then X is a 1 category. And with that setup, a tangent structure on X, in this sense, agrees with the definition stroke theorem given by Leung. So this recovers the original definition. of this work then, so this is our theorem, and of course it's still in progress, in the sense that we haven't written down all the details yet, but I feel like I have enough of the framework for me to be able to tell you about it. So I want to take X to be a category of presentable infinity 1 categories. So maybe I should have said what C was first, I guess. So C is the infinity 2 category of infinity 2 categories. And then X is the infinity 2 category of presentable infinity 1 categories. So I have the presentable infinity 1 categories, I have functors that preserve filtered colimits, and I have natural transformations, so that's I form an infinity 2 category. And so the theorem is that then I have a tangent structure on X. So there is a tangent structure on X. And the underlying functor is exactly the functor I described before. So C is this category of excisive functors from finite spectra. And the rest of the structure is as I described it. So
particularly, you're proving this pullback properties. Can you say what that means?
That's what I'm going to do right now. Yeah. So again, a lot of this structure is fairly simple to write down and verify that it certainly looks like it has all the properties you would expect. But the part that really made me find this more interesting is that there's this sort of deeper analogy between manifolds and calculus of functors. So I need to say the corresponding lemma then says for any C, so for any C in X, so C is a presentable infinity 1 category, there is a pullback in X that looks exactly like it did in the previous lemma, in the version for manifolds. So let me try to explain why this lemma is true. Or actually, let me try to explain what is it saying about Goodwillie calculus. Because that's again, really, I think the reason that I'm enjoying this project is because it's actually getting me to look at questions in Goodwillie calculus that I hadn't previously thought about, and that somehow are quite simple questions, but still interesting to figure out. So in particular, so what is the substance of this lemma in the context of infinity categories? Given, so I want to understand this double tangent bundle. So this is, you think of this as the category of functors from 2 copies of finite spectra to C that are excisive in each variable separately. So let's start with one of those things. So excisive in each variable. And so now I want to sort of look at this pullback. And so essentially what I'm doing is trying to explain why this pullback makes sense on the level of objects. So an object here is a functor like this. it maps to the zero section. The zero section was a constant functor. So saying it maps to the zero section is saying that if I plug in the trivial spectrum for the second variable, then the functor I get is now constant. So this is a constant functor. So for all, right, so this is for all a, I guess I should put a dash here or something. So this, as a functor of its first variable, this is a constant functor with some value.
Point.
Sorry, which is the value of x is f. So, you know, the functors that are reduced and excisive in each variable are classified in Goodwillie calculus just by a single coefficient spectrum. That's one of Goodwillie's main results, is classifying functors that are reduced and excisive in each variable, multilinear functors. So here we have a functor that is excisive in each variable and sort of reduced in a sense in one of its variables. And the lemma is giving us a classification of those things, and in fact, you work out what this lemma says about such an f. It says that it has to split. So given f, there is a splitting. So f of a b splits as f of star b. So the value when I put the other variable as trivial splits off. And what I'm left with is the homotopy fiber of the projection map there. So this is sort of a homotopy fiber of x. And there's a little more that this bit is multilinear. So this is multilinear, and hence this is equivalent to h of a smash b for some decisive h. All right, so there are sort of two parts really to what this lemma is saying in the context of calculus of functors. It's saying that this sort of 1-1 excisive functor splits, and what's left over is multilinear, and multilinear functors factor via the smash product. Okay, so putting both of those pieces together gives you this lemma. So, you know, I don't know. I don't think this is, I mean, it's not a particularly deep result about Goodwillie calculus. It's not that hard to prove once you figure out what it's really asking. But it is something that I had never thought of before, and so, you know, again, I'm enjoying learning things about Goodwillie calculus that I didn't previously know from answering questions about this tangent structure. Okay, so I've got 5 minutes or so. And so I just want to try to talk a little bit about what you might call applications. So why are we doing this? Why am I interested in getting this tangent structure? Well, you know, I think it's helpful to have a kind of enhanced intuition for this analogy. So you know, Tom Goodwillie has been sort of telling me for years how to think about functor calculus by analogy with manifolds, and he has an intuition that goes far beyond mine, and having a concrete framework like this is certainly helping me to understand a lot more of the ways of thinking that he's been telling me about. So I like having this more precise analogy with ordinary calculus. And my hope is that it will also suggest, it will help us learn more about functors and suggest new questions or directions to go in by sort of transporting ideas from ordinary differential geometry into, via this tangent structure into the calculus of functors. So let me just finish by going through a few ways in which that, things we've already sort of thought about to varying levels. So first one is what's called differential objects. So this is something that Cockett and Cruttwell define in any tangent category. So in any tangent category, Cockett and Cruttwell define differential objects, and these are just the things, the analogues of vector spaces. They're the things that have tangent bundle that is just tangent bundle of M is M cross M. And so as I pointed out earlier, the stable infinity categories play this role. Okay, so this makes more precise this notion of manifolds. These are just category of manifolds. This is just the vector spaces in category of presentable infinity categories. These are the stable infinity categories. So again, it makes that analogy between vector spaces and the stability condition more precise.
This is by any map over M or Robinson conditions?
I'm sorry?
Is this by any map over M?
There are more conditions. Yes, there are always more conditions. So that's one of the pieces of being a differential object. Okay, so then the second part, which is the part that I sort of really made me think this is something that could actually connect to Goodwillie calculus, is to think about higher order approximations, okay, and so which in ordinary calculus you sometimes call jets or n-jets. So in any tangent category, we can say when two homomorphisms agree to order n or determine the same n-jet at a particular point. So we can say they have the same n-jet at some point. So now a point is going to be some map from the terminal object into M. If the same n-jet, if f of x is equal to g of x, and when I look at the n-fold tangent bundle at this point x, going to say y, f and g determine the same map on this fiber of this n-fold tangent bundle. So t and f is equal to t and g. Okay, and so I can make a version of this definition in any tangent category, and so then the theorem is that in the example that we've constructed, a natural transformation from alpha from f to g induces an equivalence on these n-fold tangent bundles at, I'm going to take the trivial object here, let's say they're reduced because it'll make it easier. So it induces an equivalence like this if and only if alpha is a PM equivalence in the sense of Goodwillie. So this is telling you that as you might hope, n-jets in the tangent structure that we've constructed do correspond to n-excisive functors. In the sense it says that Goodwillie's definition of n-excisive can be recovered from the tangent structure. Okay, and part C was going to be about connections, which I don't really understand very well, so it's probably good that I run out of time. Thank you.
Questions?
Anyway, we're getting a Lie bracket into the game.
So the problem with the Lie bracket is that it involves a negative. So now you can do things with negatives in this context because you can subtract two things as long as you have a map between them. You can take the fiber. So I don't know if you can I don't know how much of getting a Lie algebra you can do, or whether there are other ways to do it, but certainly in the abstract tangent category setting, they do develop the Lie algebra structure on vector fields and prove some properties of that structure. So it's certainly something that we could try to do in this context, but not having
is
the negative.
the computer scientist that you mentioned?
Yes, yeah, Cockett and Cruttwell are the two mainly leading that.
Are there any interesting theorems which hold on generality of tangent categories?
I don't know. I guess it depends. I mean, I don't. So depends what you mean by interesting, obviously. Yeah, pretty much, I've told you most of what I know about tangent categories now. So I think that this is the subject of tangent categories itself is only a few years old, and certainly looking at this example is only 6 months old. So I think there's a lot of questions that we could still investigate. I don't know in particular.
Goodwillie has given arguments that the tangent space to the category of manifolds is the category of spectra. And it looks a bit like you've just built that into the definition.
Yeah, I think that's right. So certainly, I mean, this is built into the definition of the tangent category as excisive functors from finite spectra to C.
Right.
If C is spaces, say, then that is equivalent to spectra. So, or at the base point, it's equivalent to spectra. So yeah, I mean, in some sense, the stable, I mean, this theory is constructed in such a way that the fibers of the tangent bundle are stable infinite categories.
He then goes on to ask about connections and asks what the curvature of the category of manifolds is.
Yeah.
Did your part C say anything
Well,
about that?
it was going to say that there's a so again the kind of abstract notion of connection is given by Cockett and Cruttwell. That specializes to the ordinary notion of connection on a manifold in the case of the category manifolds. And so so I've started to try to think about how that carries over into this particular example. And there's a canonical choice for what the connection map might look like. So very briefly, a connection on an object M can be thought of as a map, or it can be encoded as a map like this, which is not the same as the map that appeared in the lemma, but a map like this satisfying some other properties. So we can kind of follow that process through, and there is a sort of fairly obvious guess of what a canonical connection might be on an infinity category, and the kind of sort of curious answer that I get is that connection on an infinity category C exists if and only if the second derivative of the identity on C is true. So this is the second derivative of second Goodwillie derivative of the identity functor. So yeah, you should take this with a heavy dose of salt, but there's some rough calculation that we've done that suggests that somehow the second derivative of the identity is helping to understand connections. Which sort of makes sense. The connection is a kind of second derivative kind of thing.
All right, I think I want my cookies.